All right, guys, so this is going to be our last video for section 2.8, and we're going to talk about doing those sketches. So if we're given a function, how can we make a sketch of its derivative functions graph? And we're also going to look at some notation for the derivative as well as for higher order derivatives. What's the meaning of, for example, the second derivative or the third derivative, etc. So let's start with the graphing part. So I'm sure you've seen this, and let's take a look at a few examples. So we've been given a function, so we're given an original function, and we want to draw some kind of sketch of the derivative function. We're going to see for a lot of these, we're going to sort of do an approximation. Oftentimes, we're not going to be able to tell for sure what the derivative function's graph looks like. We're going to have some sort of rough ideas. However, in this first example, note that our original function is what we would say, it's sort of a piecewise linear function. It almost looks like on all these sort of separate intervals, the value of f of x is defined by a linear function of x. And because linear functions have a constant slope, in this one, we're actually going to be able to be more precise with our graph of the derivative. All right, so let's investigate. How can we explore this? What I want to do in this case is probably kind of think about each sort of portion of my graph of f of x, aka each of these chunks separately. So, and I want to divide them up based on the x values that they exist for. So it's almost like I'm going to sort of be, inputting, I think right here, a little kind of line, and I'm going to look at, okay, what does it look like this graph is doing on the interval of from here to here? So notice like between -8 and -5, the graph looks like that. My next interval takes me about from -5 over to x equals 0, because it looks like that's sort of a constant function or a constant linear function on that interval. And then we have a linear piece that goes from x equals 0 to x equals 4. So let's kind of take apart that interval. When we've got the piece from x equals 4 to x equals 7. And then finally, we've got this piece that appears to go on from 7 on to infinity. Now, notice, as we said, that on each of these pieces, the function happens to be linear, right? So that means that we can actually describe the slope of the function on each of these pieces. And in fact, we can find the slope probably just by counting boxes. Now, remember that when a function is linear or linear on a piece, if you were to draw a tangent line, for example, at any piece along this function from x values to -8 to -5, the tangent line would actually just be the line of the function itself. There's no difference between the tangent line and the function because the function there happens to be linear. All right, well, remember that the graph of the derivative, how does the graph of the derivative relate to the graph of the original function? We want to recall that on the graph of f of prime of x, on the graph of the derivative function, the height of each point corresponds to the slope of the tangent line, on the graph of f of x at that value of x. So it's a little bit, something to wrap your mind around, but essentially what we're going to see is that when we make our derivative graph, all of the points on our derivative graph's heights are actually going to equal the slopes of the tangent lines on our graph of the original function. All right, so let's take a look at this. If we look at this interval from x being -8 to -5, let's see if we can assess the slope of this line in there. Since it's constant, I can sort of find it anywhere in here and it's going to be the same. It looks to me like if I count this point and this point, the slope appears to be, down 2 units to the right 1 unit. So I'm thinking in this little interval, it appears, let's get a darker green here, it appears that on this interval, the slope, and I'm just saying the slope, not even the slope of the tangent line, because in fact on that interval, the line is a line, or the function is a line, it appears the slope is -2/1 or simply -2. It was down 2 to the right 1. All right, well, let's do the same thing for the interval of x values from -5 up to 0. Again, since it's a linear function on here, I can assess the slope at any 2 points on here. So I'm just looking for essentially places where it goes through a corner. And it looks to me like here and here will do the job. And it looks like we go up 2 to the right 1. Up 2 to the right 1. All right, so that would mean here the slope is equal to +2/1 or +2. On the next interval, it appears that the slope is down 1, right 2, down 1, right 2. That gives me a slope of down 1, right 2, -1/2. On our next interval, it appears that the slope is down 1, 2, 3, 4, right 1, down 1, 2, 3, 4, right 1. Okay, so in this interval, we have a slope of -4/1 or -4. And finally, on our last interval, well, this is just a horizontal line, aka a constant function on this interval. And I can see that the slope of a horizontal line is always just 0. So this, in fact, is basically going to give me all the information I need in order to plot my derivative function. Since I know, for example, that between -8 and -5, the slope of my original graph is always -2, well, when I go to graph my derivative function, that's going to mean between -8 and -5, the height of my derivative function should be -2. Okay, so let me do the derivative function. How about in black? What do I know? I know that from -8 to -5, the height of the derivative function should be -2 because that was the slope of my original function on that interval of x values. And in the next interval, from -5 to 0, well, there my slope was +2. So on the interval of x values from -5 all the way to 0, we had a constant slope of +2. Now you might be wondering, what about our endpoints and our corner points? Well, let's address those. This point right here is certainly in the domain of our original function. Can we talk about the slope of the tangent line at that point? Not really. Clearly, like if we let our second point come in from the right, it has the same slope, and therefore the limit as h approaches 0 of the tangent line fraction would be, as h approaches 0 from the right would be defined. But then I don't have anything over here. I'm not sure I can really define the derivative there. So to indicate that on the graph of my derivative function, I'll just put an open circle at 8. Similarly, can we define the tangent line slope at -5? Well, we know the derivative doesn't exist here. We did a video with examples and we saw this as a corner. So what's that going to mean? It's going to mean that -5 is not a value in the domain of my derivative function. That's going to mean that both of these points get open circles because -5 is not a number for which f prime of x exists. Well, similarly, when we get to 0, we also have a corner, so I can just get myself ready and put that there in as well. All right, on the next interval of x values from 0 to 4, our slope was -1/2. That's going to mean that my derivative graph has a height of -1/2 for all values of x between 0 and 4. So that's my best job at graphing a height of -1/2. It doesn't really look like a line, but bear with me. Then what happens? Well, between 4 and 7, we have a slope of -4. So that's going to look like this on the derivative graph. And finally, after x is bigger, as soon as x is larger than 7, we had a slope of 0 on our original function. So that's going to mean as soon as x is slightly greater than 7, the value of the derivative is 0. And that looks like it's going to continue. So notice here, what we have now is a graph of our original function up above and a graph of its derivative below. Let's label this guy. This is the graph of f prime of x, such that if I take any point on my graph of f prime, for example, this point right here is the point -4, 2. What does that point tell me? It tells me that for the x value -4, the value of the, the value of the derivative at that value of x, aka f prime of -4, which remember means the slope of the line tangent to my original function right when x is -4, has to be equal to 2. And of course, we see that that in fact is the case. So in this one, we actually were able to get a pretty precise graph of our derivative because our original function was piecewise linear. That's not always going to be the case. Let's look at a few more examples. All right, so now we've been given a function g of x that looks like it might be a cubic function. It's impossible to really tell from what we see, but we also don't even have any scale on the y-axis. So I have no idea sort of if this is going by ones, or maybe this is 500 and this is a much larger scale on the y-axis than the x-axis. We're not going to be able to be precise here. In cases like this, when we want to graph the derivative from the function, we're going to look for key features. And essentially, we're going to look for places where is the derivative function going to have a height of 0? Where is the derivative function going to have a positive height? Where is the derivative function going to have a negative height? And sort of in what direction will it be going? All right, so let's take a look at that. Now, remember that your derivative function tells you the slopes of the lines tangent to this function. A good way to start is often to look for places where either the derivative function is not going to exist or where the derivative function is going to have a value of 0. So I'm going to start with that. I'm going to look for places on f of x where f prime of x either would not exist or where f prime of x would equal 0. And remember that f prime of x measures the slope of the line tangent to f of x. And therefore, for f prime of x to equal 0, we would need a horizontal tangent line. So I start, in this case, by looking for those things. I'm going to notice that, if I think about this guy, this graph doesn't appear to have any issues. There are no cusps, there are no corners, there are no sudden breaks in the function, there are no discontinuities, there are no vertical asymptotes, there's no vertical place on the function or vertical tangent lines. I think that in this case, f prime of x is going to exist for all values of x along this function. So let me go on to thinking about where would f prime of x be 0? And the easy way to do that is to look at your graph of f of x and imagine where, if you were drawing in little tangent lines here or there or here or wherever, where would those tangent lines be horizontal? Where would we have a flat tangent line? Well, I can see that actually I would have a flat tangent line right there. Similarly, down at this valley here, I would have a flat tangent line. Momentarily, the function would have a tangent line with a slope of 0 there. So I'm just going to note those maybe in red for myself, and I'll do my best here, but again, you know the drill with me drawing. All right, so I'm just sort of noting with these little lines here, some tangent lines. And what I can see is with each of those tangent lines, I have what I would consider m tan here is equal to 0. What's that going to mean? It's going to mean that on the graph of the derivative of this function, whenever x is -3, or it looks like 5, the height of the graph of the derivative function will be 0 because the height corresponds to the slope on this function. So let me just plot those zeros now. And in fact, maybe I'll even sort of make a few lines, and I tried to line this up, but of course I probably didn't. I'm just putting these in for a visual here, and I'll put them in on my graph below just so I kind of have it marked off at -3 and at 5. So these are not on the graph of any function, they're just trying to help me kind of keep myself organized here. All right, so what do I know? Well, I know that the graph of the derivative function is going to go through the point -3, 0, and I also know it's going to go through the point 5, 0. So I have 2 points on the graph of my derivative function already. Okay, I think those are the only 2 points as I travel along this function where I would have a horizontal tangent line. So let's now consider what happens on the interval to the left of -3. Let's consider what happens on the interval between -3 and 5. And let's consider what happens on the interval from 5 up to positive infinity. Well, if we zoom in and we think again about drawing in little tangent lines here, and you can actually draw them in if it helps, it helps me a little bit to picture them. So I'm just gonna, make a few points, and because I have no scale on the y-axis, I certainly can't get an exact value of the slope of any of these tangent lines, but drawing them in helps me discern what's the pattern. Are they positive or are they negative? Are they getting steeper or are they getting more gradual? So what I see is on this interval from -infinity to -3, as far as x values go, it looks like I've got positive sloped tangent lines. All of these lines are going up from left to right, so they would have positive slopes. And they start out very steep. The further we go to the left, the steeper these things are going to be. They start out very steep, and they're getting gradually less steep, and that means in terms of slopes of lines closer to 0. And then, of course, right at x equals 3, they equal 0. So what I can say about the tangent lines in this region are the tangent lines are positive, and they are, I should say, the slopes of the tangent lines, not the tangent lines themselves. Slopes of tangent lines are positive, and they're getting less steep, which means that they are getting closer to 0 as we get closer in terms of x values to -3. Well, what does that mean about the graph of my derivative function? It's going to mean, since I know that for all values of x to the left of -3, the tangent lines have positive slopes, that's going to mean that the graph of my derivative function has to have y values that are positive on this interval to indicate the height of each point. Again, remember, tells me the slope of a tangent line here. What do I know? Well, I know the y values are all positive and they're getting closer to 0. Oh, and yeah, right at -3 is where the y value should be 0 on the graph of the derivative, because that's where the slope of the tangent line to my original function is indeed 0. All right, well, I can't do anything sort of more specific than this, but what I can say is I know that I have positive y values all the way up here, and that as I approach an x value of -3, the y values on this graph are getting closer to 0 because the y values on this graph are in fact the slopes of these lines, and they are getting closer and closer to 0. Okay. What about in this next interval of values? If we zoom in again and we sort of imagine ourselves taking off here and drawing in some tangent lines, well, now we notice something a little different. Now, if I think about the slopes of all of these lines that I'm drawing in, they're all negatively sloped, right? They're all going down from left to right. And I might also notice about their steepness. If I take a look at, maybe I'll do these in a different color just for a visual. If I take a look at sort of what happens as I start moving over here, it's sort of negative but gradual, still negative getting steeper, negative getting steeper. It almost looks linear on this part. It's hard for me to draw a tangent line that isn't just covering up the function. But it certainly looks like if I sort of break this up maybe into two little regions here, and this is me just again drawing in some random line, what I'm noticing is that, between here and here, it looks like my slopes are all negative, and not only are they negative, they're getting steeper, which would mean that the numbers are getting further away from 0 as far as what the slope is, which means they're getting more and more negative. So I see on this sort of little sub-interval that I've created that in here, the slopes of the tangent lines are negative and are becoming more negative because they are getting steeper. They're becoming negative numbers that are larger in magnitude. Note, like right here, the slope might be -1/2, and then here the slope is -1, and then by the time I'm here, the slope is -1.5, and then maybe here it's -2. Okay, so how would I draw that here? Well, it looks like basically between, it's hard to tell exactly where they stop getting steeper, but kind of looks like what's going to happen on the graph of my derivative function. Well, if I'm trying to plot all of these slopes as the heights of points here, it kind of looks like they start out negative but close to 0, and they get more and more negative as I sort of come this way. All right. Well, that seems like it might do something like this. And again, we don't really have any sense of scale here. I'm just going to go like this. Well, then what happens? Then if I zoom in again, it kind of seems like we sort of reach our, ultimate steepness somewhere around there. And if I then continue to draw tangent lines, well, then they start to get less and less steep again. In fact, they start to get more and more gradual as I approach an x coordinate of 5. It's hard again to draw these lines and make them look separate from the graph itself. Notice that I'm easing up. My tangent lines are going from steeper to less steep. Now they're still negative, but they appear to be getting less steep, which would correspond to them getting closer to 0, aka less negative on the graph. So here we have the slopes of tangent lines are negative and getting closer to 0. Well, how am I going to represent that on the graph of my derivative? Well, my slopes are negative, but now they're starting to get less negative. They're starting to get closer to 0. maybe that's going to be something like this. And again, this is, you know, an approximation. Okay. Well, let's look at that last region of our original function. Once I hit an x-coordinate of 5, we know that we saw the slope of the tangent line there was 0. What happens as we look at points to the right of an x-coordinate of -5 and sort of start to draw in some tangent lines? Well, what do I see? I see now, again, that all of these tangent lines that I could draw in now have positive slopes. And I see that the slopes are going from a very shallow slope early on, and they're getting steeper and steeper and steeper and steeper. And if I were to continue on, they'd be getting steeper and steeper and steeper. So what does that tell me about the values of the derivatives over here? It tells me that they're going to be positive and they're going to grow from 0 and get larger and larger and larger. What we can say is over here, the slopes of the tangent lines are positive and getting more positive. What is that going to mean as far as my graph of the derivative? Remember, on my derivative, the height of every point tells me the value of the slope over here. So right when x is almost, next to 5, when x is 6, well, there it's positive, but it's not like super positive. Maybe it's got a slope of 1 or 2 or something. And as I get further and further to the right, it gets further higher and higher. Well, the best I can do is maybe something that looks like this. Notice now a nice relationship here. I now have a graph of my derivative function as best I can do, and I might want to notice something kind of cool. Notice that, in fact, f of x looked like a cubic function to the naked eye. And what does f prime of x look like? Well, to me, it looks like a parabola, which is a quadratic function. So something to pay attention to. In fact, we will see that if you have a polynomial function, the derivative will always be a polynomial of 1 degree smaller. So it's actually not a coincidence that we started with a graph of f of x, which appeared to be a cubic function. And when we did a rough plot of maybe what f prime of x would be, we get something that looks like a quadratic function. That, in fact, will always be the case. If we start with a 4th degree function, the graph of the derivative will be a cubic function. All right, let's look at one more. Now, the function graph here is the natural log function, everybody's favorite, natural log of x. And this function, again, the graph is kind of hard to see, but it has a vertical asymptote at x equals 0. It just goes down here forever. And then going this way, it does go up forever, but it's kind of going up super, super, super gradually. It basically goes up at a very gradual slope. Well, again, we don't really have any scale values on here. I don't know how far we're looking at, but we can certainly assess, what are the sort of relative slopes of the tangent lines to this graph. Now, once again, I might start by thinking about, are there values of x for which either the derivative f prime of x will not exist, or where f prime of x will be 0, aka a horizontal tangent line. I'm going to put HTL for horizontal tangent line. That's going to be something we talk about a lot, and nobody wants to write that a million times. Well, if I kind of scan this graph looking for a horizontal tangent line, it looks like I'm sort of approaching a horizontal tangent line over here. However, there isn't any place where this is going to have exactly a horizontal tangent line. However, there are certainly a lot of places where f prime of x is not going to exist. Notice, since the graph doesn't exist to the left of 0, or even for that matter at x equals itself, certainly the derivative is not going to exist over there either. So we basically can tell just by looking at this that essentially for x less than or equal to 0, neither f of x nor f prime of x will exist. Remember that for f prime of x to exist, f of x has to exist at that point. Okay, so that's going to mean the graph of my derivative similarly will not have any action going on over here. All right, well, let's see then if we can assess kind of what we notice on our graph right here. Let's start by just kind of zooming in and trying to, imagine us drawing in some tangent lines. And again, this is going to be a nightmare because it's going to be impossible for me to draw tangent lines that don't actually look like this function itself or sort of cover it up, but I'll do my best here. So I'm just kind of making a few points and I'm drawing in some what to me look like somewhat of tangent lines. And I want to be thinking about the slopes of these guys, right? So I look at this one, I can tell that m is like positive. This is a really steep slope and it's a positive slope. That's going to mean m is positive and very large, right? We get steep slopes when we have numbers that are large in magnitude. So m is positive and very large. And what happens as we kind of go further and further to the right? Well, it certainly looks like we still have positive slopes, but it kind of looks like they're becoming more gradual. So I'm just going to note that sort of for all of these guys here. So we still have positive slopes, but they're becoming more gradual. Which means they, in value, are getting closer to 0. Well, if I look a little further on, does that same pattern kind of continue? If again, I kind of try to keep drawing in little tangent lines here and look at what happens as I move from left to right. Yeah, it kind of looks like to me that we still over here, kind of in this whole area, if I look at these lines, these tangent lines, it looks to me like we still have positive slopes. Slopes are still positive, but getting even more gradual, meaning getting even closer to 0. Now, it looks to me like we're never actually going to get a tangent line with a slope of 0 on this graph because I know that the graph of ln never truly makes it horizontal. It keeps going up. It just goes up more and more and more gradually. All right, maybe we have enough information now to draw a somewhat decent sketch of our derivative function. Well, what do we see? We saw that initially for very small values of x, m was positive and very large. So that would mean I'd have points here that were very high. When x is close to 0, the height of the point would be a very large positive number because it corresponds to the slope of that tangent line. As I get closer to the x value 1, what happens? The slopes are still positive, but they start to get smaller. So I would have something where my values of my slopes were coming down. Let me just plot a few points here. So maybe I have something really high up here. It's getting a little lower as I get closer and closer to 1. And then what happens? Well, then we again still have positive slopes, but they're getting, here the slope was sort of, it went down very quickly there. And now it's still getting more gradual, but it's kind of getting more gradual, maybe at a slower rate. So maybe we have something where it's getting lower, getting closer to zero, closer to zero, closer to zero, but it's never actually hitting zero. Connect these points in a smooth line. And in fact, maybe I should have used a different color for this. Oops. Let's take that back and do it in blue. Okay. And what we get is maybe a graph that looks like this for our derivative function. Well, what does the graph of the derivative function kind of look like? Kind of looks like a piece of the 1 over x function. In fact, it is. So we'll see that soon enough. But yeah, notice that I'm not doing anything super precise here. All I'm doing is basically putting the heights of points on the graph of my derivative function either above the x-axis if the slopes were positive, or in this case there aren't any, but below the x-axis if the slopes were negative. And the height of these points is somehow corresponding to the steepness or the values of the slopes on the original function. All right, so hopefully that gives you enough to go through some of these examples. Remember, you don't have to be super technical. Look for those horizontal tangent lines. Look for where do I have positively sloped tangent lines? That means your derivative is going to have positive y values at those points. And where do I have negatively sloped tangent lines? That's going to mean that your derivative graph has y values below the x-axis, negative values at those values of x. All right, let's consider a little bit of notation around the derivative. It's kind of a pain to keep writing the derivative, etc. And we want to recognize several different notations. In fact, there's like a million of them, of course, like there is for most things in math. But perhaps the good news is, although there are a million you could encounter, generally there's going to be like 2 or 3 that we see most often. So I made a little list here. In the list, I sort of put, if the original function is expressed like things in this column, then ways in which the derivative function might be expressed are the things in this column. So in general, if you see, this, you're not going to see this derivative notation. You're going to see this or this, okay? So essentially each notation over here has a potential, way that we would notate the derivative if this was how the original function was notated. So we've already seen that if the original function is called f of x, well, one of the ways that the derivative is notated is as f prime of x. That's the one we've seen already. I'll just put little arrows between these to show that they kind of go to one another. However, there's more different notations we might see for that same original notation for the function. Sometimes when we want to say, okay, the original function is f of x, we notate the derivative as simply d dx of f of x. What does this d dx mean? It means the derivative, and the bottom means with respect to x. And you might be thinking, well, with respect to x, why do we need that? In truth, we need to know when we're taking a derivative what variable we're taking the derivative with respect to, because soon enough in Calc 2 and Calc 3, you're going to have functions that involve multiple variables, and it's going to mean something different to take the derivative with respect to x, whereas if we had also a b in our equation, to take the derivative with respect to b would give us something different. So this symbolizes to take the derivative with respect to x. And this is another notation we might see, and I would read this as the derivative with respect to x of f of x. Well, we kind of get the same idea when we go to this notation. If we start with f of x, another way the derivative could be notated is df dx. It's almost like they just took the D and the F part. You know, when we talk about a function f, sometimes we call it f of x. Sometimes we just call the function f and we mean f of x. Well, we can also see the derivative notation in this way. So again, this means the derivative here of the derivative, the bottom, the dx part means with respect to x. And here we have of the function f. So it's like we're just calling the function f instead of f of x. Now, we also sometimes see, this is kind of older school notation. If the original function is f of x, we can sort of see this big D in front of f of x, and that just means the derivative of f of x. Sometimes it's a big D with a little x subscript. Well, that just indicates, again, the derivative with respect to x of f of x. These are kind of not commonly, not used as frequently. So I wouldn't worry too much about them. I never write them like this. However, you may see it sometimes expressed like this in your textbook or on WebAssign, and you should be familiar with what this thing means if you see it. Well, what if our original function isn't called f of x, but maybe we just have the notation y, right? A lot of times we just notate a function with y. Well, if we're using the notation y to represent the outputs of our original function, then the derivative function sort of can come in two ways. We can call it y prime, so we would call this guy y prime. And that's the same thing as we say here. Essentially up here we say, f prime of x. We've had that notation. It's the same corresponding notation, but instead of f of x and f prime, we're using y and y prime. People often really like this notation because it's really efficient, right? It's done. Similarly, we get the sort of corresponding notation that we saw here and here, where we can have this ddx of our function. Well, if we call our function y, then the derivative can also be represented as this like ddx of y. And so we would read this guy as, again, the derivative with respect to x of y. That's what it means here. Basically, it's like almost like you're doing this dx of y. And we read this guy sort of in layman's terms, we read it as dy dx. That's just how we say it. So if you ever hear dy dx, it's talking about the derivative of the y function. All right. Well, let's also consider the fact that we're going to see in chapter 3 in particular, we're going to learn how to take derivatives of functions. And so we're going to often think of the derivative not just as like the resulting function we get, but we're going to think about taking the derivative function like a verb. It's an action to take the derivative of something. In fact, it's called differentiating. And so we're going to have some terminology and some notation that indicates sort of take the derivative of this function. It's going to say, well, we're going to take the derivative, we're going to differentiate this function. And why not see some of it now? So one of the ways to interpret this, now of course it can be read as the derivative with respect to x of f of x. And notice I put over here equals f prime of x. On the left-hand side, this kind of indicates an operation. It's like the ddx, the derivative with respect to x, is acting upon the function. This is sort of how we would indicate we're going to take the derivative with respect to x of the thing in here, f of x. And once we do that, what we get is in fact f prime of x. Similarly, if I have the still f of x notation, and I want to take the derivative with respect to x of that f of x, I can write the resulting derivative function as df dx. We saw that in the previous columns. What about if I write ddx of y. Notice here, it's again kind of has that indication of an action. We're taking the derivative of this function y. Well, if we do that, what do we get? We get y prime. Another way we could write the result of taking the derivative with respect to x of y is that when we do that, we get dy dx. This is the derivative function. Another way we can indicate this action of taking the derivative without using this d dx of whatever function we have is by putting a prime outside a bracket or parentheses surrounding our function. So if I look at this guy right here, this is saying take f of x, and this prime way out here is basically saying if you take the derivative of the thing in here. So this says f of x prime. Well, what do I get if I take the derivative of f of x? I get f prime of x. What is y prime? If I take the derivative of the function y, I get y prime, the derivative function. So these notations, this ddx in front of a bracket or parentheses containing a function, again, can mean take the derivative of that thing. Similarly, the prime left outside a parenthesis or bracket can also mean the derivative of this thing is, and then you'd write the derivative function on the next line. Now, this notation helps us also get to our last topic, and that is the topic of higher order derivatives. So you may have heard in the past something called, the second derivative or the third derivative. Well, the first thing I want to take is I want to say is that whenever we talk about derivatives like we have so far, all the derivatives we've talked about and seen so far are technically first derivatives. Now, essentially, when we take a derivative and we don't call it anything other than a derivative, we're talking about taking the first derivative of some function. So if I just say, oh, the derivative is this, and then I mean the first derivative. Just like when we have a square root without the little index, we know that we mean the square root, right? So all of the things we've seen so far are first derivatives. But we do, of course, have what are called higher order derivatives. We have second derivatives, third derivatives, fourth derivatives, as far as your imagination can go. And when we're talking about one of those higher order derivatives, we have to indicate what type of derivative or what order derivative we're actually referring to. So let's take a look at it. It's somewhat intuitive. Notice if I use my notation here, the sort of take the derivative with respect to x of this thing, I notice that now I'm actually saying take the derivative with respect to x of a derivative, right? F prime of x is the derivative of f of x. So what do I get if I take the derivative of the first derivative function? Well, of course, it's just like a ladder. What do we get? We get the second derivative. How is the second derivative denoted? It's denoted by f double prime of x. So what this says is if you take the derivative with respect to x of f prime of x, which we know is called the first derivative, you get the second derivative, which we denote derivative with f double prime of x. So when we see f double prime of x, this means the second derivative of f. Now, what if we just have a different notation? What if we take the derivative, again with respect to x, But now we're taking the derivative of df dx. Now remember, this itself means the derivative of f with respect to x. So this is already the first derivative. It's essentially the exact same thing as f prime. Well, then we know if we take the derivative of the first derivative, we're going to get the second derivative. But we're going to have a different notation here. It's a little weird, and you just kind of have to get used to it and accept it. And it sort of makes sense and it sort of doesn't, but it's called Leibniz notation. And what we see is that when it's written like this, the second derivative is denoted on top. It's almost like you did multiplication. It's like you did d of df and you multiplied them and you get d squared f. So yet it's not really a square. It's just kind of easy to think about it that way. Essentially, this means the second derivative of f. And on the bottom, this is where it gets weird. You're kind of like multiplying dx by dx, but in fact, instead of writing like dx squared or d squared x squared, you just write d and only the x gets squared. Again, these are not exponents. It's a superscript. It's just a notation that has evolved over time. And essentially, if we take the derivative of f with respect to x, we get the second derivative of f with respect to x. This is not super common. I'm going to highlight the ones that are more common so we have a special attention to them. So this guy for sure. We also see this quite a bunch. This guy down here says, hey, if we take the derivative with respect to x of y prime, well, y prime is the derivative of y, we should get the second derivative. And if my function has been written in terms of y, then the second derivative will be written in terms of y as well, and it will be written as y double prime. Okay, this next one is quite a bit like the one we just saw here, except instead of calling our function f, we are calling the function y. And this actually is a really common notation. It's called Leibniz notation, and it's one you will see. And it has the exact same pattern that sort of makes sense and sort of doesn't make sense. But if the first derivative of a function is called dy dx, when you take the derivative of dy dx, you get the second derivative function. And the way that that second derivative is denoted is as d2y dx squared. Again, it doesn't really make sense. It's just a notation. What about if I have the prime outside of the bracket or parenthesis indicating to take the derivative? Well, we end up with the same results. Remember that this guy prime means the exact same thing as take the derivative of this thing with respect to x. So on the right-hand side of all of these, I would have f double prime of x. This would be d2f dx squared. This would be y double prime, and this would be d squared y dx squared. And all of these indicate the second derivative of the function. So just to sort of make a note here, this guy is called Leibniz notation. And it can be handy sometimes. We'll see it quite a bit. I would say, the three that you again are going to see quite a bit are these three. Sometimes you may see, the same versions, but with the prime instead. So I can highlight these guys as well. However, I tend to use the top three a little bit more, but sometimes writing the prime is just convenient. And I should probably back up and also say that this right here, similarly, is also called Leibniz notation. And same thing here. Just so that when you're told, oh, something's in Leibniz notation, you have a sense of what that means. Now, we don't actually have to stop at second derivatives either, right? Imagine, well now, what if we take the derivative of a second derivative? Well, guess what we're going to get? We're going to get the third derivative, okay? So we can run through these pretty quickly. The derivative with respect to x of f double prime of x is going to be f triple prime of x. The derivative with respect to x of d squared f over dx squared, so that weird notation, the pattern continues. Both exponents go up by 1. We get d to the third f dx cubed. If we take the derivative with respect to x of y double prime, we get y triple prime, the third derivative. If we take the derivative with respect to x of the second derivative of y with respect to x, we get d cubed y over dx cubed. And the same thing follows for all of the prime notation. So this would be f triple prime of x. This would be d cubed f over, oops, that should have a square there, dx cubed. This will be y triple prime, and this will be d cubed y over dx cubed. And again, all of these notate the third derivative. And maybe I should put in here, these all mean the second derivative. Now, we don't even have to stop with the third derivative. We can talk about the fourth derivative, the fifth derivative, etc. And just so we understand the notation in general, following along, and I'm going to simplify things here by just using a couple notations. If I have, f with a little 4 here, x, this means the fourth derivative. So notice that we have Roman numerals for our derivative indicator. So f with a little vx means the fifth derivative. And similarly, if I take the nth derivative, whatever it is, if I write f a little nx, this stands for the nth derivative of f of x. We can see the similar notation with y and y prime. If we have y, sometimes people put a bunch of things. Most time people still use Roman numerals. We've got the fourth derivative. Y gets a little bit trickier because, y, the fifth derivative, you don't want to think about this as an exponent. Y to the n, well, y to the n could mean a lot of different things, but in this particular context, we would say the nth derivative. And in Leibniz notation, we also have it. Remember, we can say d4y over dx to the fourth. This would be the fourth derivative in Leibniz notation. d5y over dx to the fifth would be the fifth derivative in Leibniz notation. And if I wanted to express the nth derivative in Leibniz notation, let me just shrink all this, whoops. The nth derivative in Leibniz notation will be what you expect. I have d to the power ny over dx to the n, we have the nth derivative. Now, most of the time when we start using higher order derivatives, we're most likely to see it written in terms of f, or maybe in terms of y primes if it's not a super high derivative. All right, so let's look at one practice problem just to kind of actually look at these higher order derivatives. So we've been given a function f of x, happens to be a cubic function, f of x equals x cubed plus 2x. And we're asked to find f prime of x, f double prime of x, f triple prime of x, and f, the fourth derivative of f. All right, well, in order to find higher order derivatives, we start by finding the first derivative. So let's do it. We want to find f prime of x. What we know is that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now let's just actually plug in what does this function f do. I would have x plus h cubed plus 2 times x plus h minus x cubed plus 2x all over h. And to kind of get this done quickly, I'm going to remember that I happen to know what happens when we cube a binomial. And so if I take this guy right here, I know that it's going to expand to the following terms: x cubed plus 3x squared h plus 3xh squared plus h cubed. I'm then going to have plus 2x plus 2h. And if I distribute the minus sign into the next parenthesis, I'm going to have a minus x cubed and minus 2x. And this is all over h. Now I can get rid of some stuff. So I can get rid of the x cubed for the x cubed over here. I can get rid of the 2x for the minus 2x here. And at this stage, I do notice once again that all of my remaining terms have at least one factor of h. So I'm going to factor out that h in preparation for cancellation with the denominator. So I take out an h and I've got 3x squared plus 3xh plus h squared plus 2. And at this stage, that means I can cancel the h on top with the h in the denominator. And now I think I can actually evaluate this by direct substitution. It looks like we're going to get 3x squared plus 3x times 0 plus 0 squared plus 2, which is just 3x squared plus 2. All right, so we just found f prime of x. Well, f prime of x is equal to 3x squared plus 2. All right, so we've got one of them done. Well, notice again, something kind of neat that we'll see soon enough and have life be a lot easier in our next chapter. F was a cubic function. What can we say about f prime? It's a quadratic function. What do you think is going to happen when we find f double prime? Well, the power is going to go down by 1 again. We're going to get a linear function. So let's do it. How do we find f double prime of x? Well, f double prime of x is equal to the derivative with respect to x of f prime of x, which means that, well, that means I want to take the limit as h goes to 0 of f prime of x plus h minus f prime of x all over h. Okay, well, what's that going to look like? Well, since f prime of x is 3x squared plus 2, this is going to be the limit as h goes to 0 of 3 times x plus h squared plus 2, that's f prime of x plus h, minus f prime of x, which is just 3x squared plus 2, over h. And again, I'm going to expand the numerator. So now I get the limit as h goes to 0 of 3 times x squared plus 2xh plus h squared plus 2. If I distribute in the minus sign here, I'm going to get a minus 3x squared and a minus 2 all over h, and I'll distribute that 3 in front of the first parenthesis, and I'll get 3x squared plus 6xh plus 3h squared plus 2 minus 3x squared minus 2 all over h. All right, well, now we can get rid of stuff. We've got a positive 3x squared and a negative 3x squared. We've got a positive 2 and a negative 2. And from here, I can see that I can again factor an h out of the remaining terms in the numerator, leaving me with 6x plus 3h. Okay, well, this is all over h, and now those two h's can be canceled. And I can now, by direct substitution, evaluate this limit. I'm going to have 6x plus 3 times 0, which is just 6x. So what did we find? We just found that the second derivative with respect to x, f double prime of x, is the linear function 6x. So again, notice you might be seeing a pattern here, and that's great because we're going to do these by patterns in chapter 3. Our f of x was x cubed plus 2x. Our f prime of x was 3x squared plus 2. F double prime of x is 6x. Let's find f triple prime of x. Well, what is f triple prime of x going to be? It's the derivative with respect to x of f double prime of x. Well, what does that mean? It means the limit as h goes to 0 of f double prime of x plus h minus f double prime of x all over h. Well, let's plug in our actual f double prime. We get the limit as h goes to 0 of f double prime of x plus h is going to be 6 times x plus h minus f double prime of x is just 6x over h. If we distribute, we're looking at 6x plus 6h minus 6x over h. Our 6x's cancel, and that's going to mean that we can in fact cancel the h as well. I've got now just an h top and bottom, those that we only have one term on top. So we get, the limit as h approaches 0 of just 6. And now we can just do direct substitution. There's no h in here. The limit of a constant is a constant. So what we just found is that, hey, f triple prime of x was actually just the constant function, now 6. Well, this one should actually make sense if we remember that f triple prime is the derivative of f double prime, which means that f triple prime, the value of f triple prime would always give me the slope of the line tangent to f double prime. F double prime is a linear function with a slope of 6. A linear function, it has a constant slope, it doesn't change. Its slope would always be 6. Well, hey, what is f triple prime? It's the constant 6, which is basically telling me that the slope on f double prime is always 6. All right, what about f, the fourth derivative of f fourth of x? Well, that's the derivative with respect to x of f triple prime of x. That's going to be the limit as h goes to 0 of f triple prime of x plus h minus f triple prime of x over h. Now this one looks a little weird because how in the world do I, evaluate f triple prime of x plus h? Well, f triple prime of x doesn't have anything to do with the input. It's just a constant. So what's f triple prime of x plus h? Well, f triple prime of anything is always just 6. What's f triple prime of x? Again, it's just 6 over h. So in this case, we get the limit as h goes to 0 of 0 over h. Well, 0 divided by anything is 0. So what we see is that the fourth derivative of f of x is equal to simply the 0 function. Does that make sense? Well, maybe. If you picture the graph of f triple prime of x, f triple prime of x would have a graph that looked just like the horizontal line through 6 on the y-axis. This would be, in fact, the graph of f triple prime of x. It's simply the graph of the function y equals 6. What's the slope along that entire graph? Well, the slope is 0. So if I were looking at the graph of f to the fourth of x, or the fourth derivative of f of x, well, it's just going to be the horizontal line at 0. Essentially, at every place along f triple prime of x, the slope is 0. So the slope, or the graph of f the fourth of x is just going to be the line y equals 0. Similarly, if I go backwards, remember what was f double prime? It was 6x. Well, that's just the line that has a slope of 6. I'm going to do a bad job of drawing it in here. It's like a steep thing like this. So this is f double prime of x. It's the line with a slope of 6. Notice that its derivative is then just a flat line at 6. And it's going to be harder for me to draw the first derivative and the original function. However, I do know this is cubic, this is quadratic, and then as I sort of chip away at each derivative, the degree gets lowered by 1. We get a linear function, then we get a constant function, and then we just get a 0 function. And in fact, if we continued to take higher order derivatives after this, if we took the 5th derivative or the 6th derivative, etc., all we would get from here on out is the 0 function. All right, so we've now covered it. We're done with section 2.8. We're done with chapter 2, and hallelujah, we're going to see in our next chapter that instead of needing to use this somewhat exhausting definition to find the derivative of a function, we're going to come up with some easier, efficient, strategic ways, rules that will help us find the derivative much more quickly. All right, talk to you guys soon.